Hello and a very warm welcome to the world of material sensing. My name is Robert Langer, and in this video we would like to talk about spectroscopy in general. We would like to learn more about how it actually works, what it can do and what it cannot do, and how we get from a spectral measurement to an actual human interpretable result. And here with me to have a closer look at all of these questions is our CTO Dr. Robert Brückner. Hi.
Hi, Robert.
Hi. Let's start with a very generic question. From your perspective as a CTO, what is material sensing and how does it relate to spectroscopy?
So you can get the insight into the materials and the composition by shining light onto the substance and then using the technique of spectroscopy to learn about the composition of the material.
Okay, so can we dig a little deeper and can you explain to us how spectroscopy actually works and how we get from a spectral measurement that we take to an actual result?
First, you need a light source. You shine light onto your substance you want to measure, and then a portion of the light is absorbed by the substance and another portion is back reflected from the substance. And this portion of light we can analyze and get the information or extract the information of how is the material composed of.
Okay. Cool. A term that I hear quite often is in this relation is the spectral fingerprint, the optical fingerprint. What is that and how does that actually work?
So many materials have such an optical fingerprint, either in the visible spectral region or the NIR spectral region. And in the NIR spectral region, you can really get insight into the material composition because the materials composed of molecules, for example, they have all individual optical fingerprints. So the molecular structure and the atomic underlying structure is responsible for that. And this you can measure with NIR spectroscopy.
Okay, cool. So basically the same way that you have a unique fingerprint that identifies you and I have a fingerprint that identifies me. So various substances like sugar, water, plastics, and so on, they also have their individual fingerprints.
Definitely.
Okay.
And the background is that you cannot measure the atoms itself because this would require electronic transitions in the visible spectral region, for example, but you measure the links between atoms. So this is the chemical bonds between atoms, which is the basis for a molecule.
Wow, that sounds like a very powerful technology. Can you take us on a ride, basically, what the capabilities are and what kind of applications are actually possible with this kind of technology? So
as mentioned, we need a molecular structure, basically. So it's very hard to measure atoms or atomic spectra in the NIR. It's even impossible. But all materials which are composed of molecules with a certain chemical bond we can measure. For example, all organic materials can be measured.
Okay. And now you use the term NIR repeatedly. NIR is near-infrared spectroscopy, right? So why is near-infrared so important when it comes to spectroscopy, when it comes to material sensing?
Because only in the NIR you can very easily measure the composition of the material. You cannot do this in the visible or only very limited, but the NIR is very prominent to do that. Okay.
So let's get back to the question about applications. So if I want to do material sensing, and what kind of world is open to me? What kind of applications can I actually do? And is this rather limited or is this rather broad?
This is rather broad, and you need to find really the right place to pick in because you can do many things. For example, you can measure what is this shirt composed of because there's molecular structure behind. You can measure all organic substances. You can measure food. You can measure liquids. You can measure solids. You can measure an apple and things like that.
Okay, wow, that's a bright range of things, right? And I know that from various things that we did here at Sonorix that there are many more things. There are like plastics that you can measure, there are coolants that you can measure, there are, all the things that we are interested, you mentioned food, all the things that we're interested as humans in food, like carbohydrates, sugar, water, alcohol, fat, proteins, and so on. This seems to be endless, the possibilities seem to be endless. Is there a more generic way to describe in a nutshell, if you will, what the power of spectroscopy is when it comes to applications.
So the power of spectroscopy is that you can take measurements using your hardware, using our Xenocorder devices, and then you get a spectrum back. This spectrum is rather dumb, so you can not extract lots of information out of that, just reading the spectrum itself. Then you need to apply some clever algorithms which are capable of then disentangling the spectral information and to translate it into the, you mentioned, human interpretable result.
Okay. So basically what you're saying is it's a very powerful technology. It can, the possibilities are very, very wide, and you can do a lot of things, and it's basically up to the user or to the company or person who wants to apply this to define what the application is, and then really look into, is it feasible or not?
Right.
Now, when we look into the feasibility, when we look into is it possible or not, I'm pretty sure there are also some limitations, right? What it can not measure, or where specific boundaries are that are really, really tough to overcome.
So it's not about the material composition, it's more about the concentration. So for example, as long as you have some molecular structure, you can basically measure it using NIR spectroscopy. You have limits when the concentration is too low, for example, for gases. Even water vapor in the air is very highly diluted, so it's hard to measure that. So you need a certain concentration of different ingredients, and then you can even disentangle or distinguish between these different ingredients in one matrix.
Mm-hmm. Now, other things that I know that are really hard to do, you mentioned very small concentrations. Other things that are hard to do are metals, for example, and salts, for example. Maybe you can comment on this, why this is so tricky, or why this is even impossible.
Well, metals are not molecular structured. They are atoms. They have also their individual fingerprint, but they are highly reflective. It's not impossible to measure metals, but it's not the best to measure metals.
Okay. And one thing that is obviously of very high interest in 2020 is bacteria and viruses. We get a lot of questions about this. Now, this is also not so easy, and NIR spectroscopy might not be the ideal tool to do this. Why is that?
Again, it's about concentration. So if the concentration would be in the right level, we could measure it. But fortunately, the concentration is not too high, so we cannot get our hands on that.
But okay, so spectroscopy still seems to be a very, very powerful technology. Can you tell us a little bit more about the requirements that you need in order to do spectroscopy, and what kind of conditions need to be there to do proper spectroscopy and material sensing?
So at first you need the proper hardware. So usually this is a big device standing in laboratories, and it costs lots of money. So we at Xenorex, we developed a very small handheld devices which are able to get the spectral information of the material you want to sense. This is first. Second, you need to make sure that you can measure enough samples at a certain environmental condition. And the third, you need to then analyze the spectral data, which are not smart at the very beginning, but you need then to apply algorithms, chemometric algorithms, in order to extract the information you want, and then to refer it to the actual reference value you are looking at.
Okay, so let's focus on two things that you actually mentioned earlier, because we now learned the hardware is here, it's miniaturized, it's way cheaper, and it's ready to be taken out of the lab basically into the real world. Now, when we enter the real world, there are obviously some environmental conditions, and you briefly touched on this in your previous answer. Why are environmental conditions important, and what are maybe the top ones that someone needs to consider?
So basically, if you shine light on a sample, you need to make sure that only the light you shine on the light with your system is analyzed. So for example, false light coming from the sun can have impact on your results. But also the temperature, if the temperature is varying while measuring, this can be tricky. You need to connect all of these environmental conditions to the chemometrics itself, so to the data science, because you can account for many effects and you can correct them. So, for example, the temperature, you can measure your substances at different temperatures, and then you can get a more robust model, and robust in the sense of it's not so sensitive on different temperatures.
Okay, so let's dig a little bit deeper here in this chemometrics field. Like, what is chemometrics? What is it good for? And what is that model you just talked about?
So a chemometrics is basically a statistical mathematical approach taking lots of input data, which are different kind of spectra from your substance, and which then extracts the differences and relates it to certain reference values. And you have many things, many algorithms and paths to go, and you need to find the right one for the right technology, because all of them have different optimization criteria. For example, you can go for more robust models. Then, for example, environmental variations can be better accounted for, and the trade-off is that you give a little bit of accuracy on the other hand. But for example, you can also go, if you have really good conditions which are not changing, you can go for really high accuracy models. So, and all of this can be controlled with chemometrics.
Okay, so basically chemometrics is a statistical mathematically approach that allows you to analyze the spectral data, and you have certain parameters that you can, focus on or not focus on in order to achieve the result that you're looking for. Okay, so these models that you're talking about, they are basically the algorithms that you would apply to a certain set of spectra in order to get to the result, to the human interpretable result.
Exactly.
Okay, because beforehand you basically have just spectra that
you have different numbers, and you have no connection to the analyte you want to analyze.
Okay, yeah, interesting. Now, when we come to the reference values that you talked about, why is that so important, and how do they relate to the actual spectra?
So if a substance is NIR active, this is what we call, if you can measure it basically with NIR technology or not, then you will find certain features in the spectra which you can analyze. And then the task of the reference values is that you can link these changes in the spectra to this reference value. So you need to have this reference value for your application. For example, when you want to measure the sweetness or the ripeness of an apple, then you need, of course, to have the reference value in advance. So some other technologies need to be applied in order to extract this value, and then you can refer to your NIR, and then you can transfer it to another apple, to an unknown apple.
Okay, so so reference valuing or applying reference value basically means having a spectra and tagging it with a certain value of this spectra equals that amount of sugar or that amount of water.
Exactly.
Okay, so now when we talk about this, then it obviously also becomes clear that spectroscopy is not I take one spectra and get all the information and get a complete model out of it kind of technology, but it's more a technology where you need a lot of spectra. The more spectra, the better for a more robust
Exactly. This is what I meant with, it's a statistical approach, the chemometrics. So statistic only works if you have lots of input data.
Wow. That was quite an intense ride through spectroscopy. Well, thank you very much. I think this is concludes a very good overview of this video. And if you would like to learn more about spectroscopy, if you would like to learn more about material sensing, then feel free to go to our website, cenorix.com, go to our social media pages, LinkedIn, Facebook, YouTube, and especially sign up for our free Explore and Understand program that provides you with a lot more information about spectroscopy and Cenorix technology.